Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Properties of Solar Cell Materials from the paper Energy Related Materials. So students, let us discuss the main points which will be covered in this module. First, we will discuss about the conduction band and the valence band. Second, the electron and the hole concentration. Third, we will also discuss about the effective mass and the effective masses of electrons and holes. Fourth, we will discuss about the impurities concentration. Lastly, we will discuss about the Fermi level and the Fermi energy. Let us start with a brief introduction about the module. We will be discussing all the properties related to the semiconductor materials which are required for the design and the fabrication of efficient solar cell systems. Solar cell fabrication and the modeling requires a detailed knowledge of materials parameters and the semiconductor properties. A brief overview of the semiconductor properties which is relevant to the solar cell is described here in detail. Basic structure of an atom. Now students, let us begin with the basic structure of an individual atom. According to Bohr's atomic model, an atom consists of a nucleus and a shell or orbit. The nucleus is composed of protons and neutrons, and the electrons revolve around the nucleus in shell. The neutrons in nucleus are neutral particles, hence the atom is composed of equal number of positively charged particle, that is proton, in the nucleus and negatively charged particles, that is electron, in shells. So the atom remains neutral from outside. Now let us consider a simplest example of hydrogen atom whose atomic structure and energy models are given in the figure below. The hydrogen atom has one atom consists of one electron in a shell and one proton in the nucleus. Electronic shells. The electrons which revolve around the nucleus, they can only revolve in the discrete energy levels or say shells. These shells are designated as K, L, M, N and so on. As shown in the figure, the electron is situated in the K shell. Considering, now students, let us imagine that the electron is situated in the K shell. So in order to move from K shell to the L shell, electron required 10.2 electron volt amount of energy, and in order to detach it completely from the atom, it requires 13.6 electron volt amount of energy. This energy is called as ionization energy or E infinity. The transfer of electron from one shell to the another occurs under the emission or absorption of electromagnetic radiation. The figure shows the schematic of the emission and the absorption of light during the electron transfer from K to L shell. So, as shown in the schematic of the absorption of light, when a solar radiation hits the atom, the electron in the K shell shifts to the L shell and the solar radiation got absorbed. This process is called as the absorption of light and is shown in the right side of the figure. Conversely, when the electron comes back to the K shell from the L shell via releasing energy as the photon, this process is called as the emission of light, which is shown in the left hand side of the figure. Structure of electronic materials. Furthermore, students, most of the photovoltaic materials, they can be described in two categories, that is crystalline and amorphous semiconductor materials. Crystalline materials are characterized by the periodic arrangement of the atoms of which they are composed. Amorphous materials, they do not have any periodicity in their atomic arrangement, that is, the atoms are arranged in the irregular manner. In crystalline materials, the periodic arrangement of atoms can build the entire crystal structure by their repeatedly stacking of small subsection in an ordered manner. The smallest possible such section which can build the entire crystal structure is known as primitive cell. Such primitive cells contains all the information about the crystal structure such as atomic positions, lattice constant, number of atoms in the unit cells, etc. Now the below figure, that is the part A, shows the atomic arrangement in the face-centered cubic unit cell, and the part B represents the schematic or the primitive cell for the same atomic arrangement, that is the face-centered cubic unit cell. As shown in the figure A, here A cap, B cap and C cap, they are the unit vectors along x, y and z axis respectively. So the length of the edge of the unit cell is called as lattice constant. The orientations of crystal planes within the crystal structure can be used to describe with the help of Miller indices. Now, the orientation of crystal planes in crystal structures can be understood with the help of Miller indices. Now, as shown in the figure on the right hand side, it can be seen that the intercept along x, y and z axis are 2, 2, 2 atoms from the origin. So now if we take the inverse of these intercepts, it gives 1 by 2, 1 by 2 and 1 by 2, which after multiplication by least common factor provides the smallest integral of 2, 2 and 2. Hence the plane can be expressed in Miller indices as 2-2-2 plane. So students, till now we have discussed about the structure of electronic materials. Here we will be discussing the origin of the energy levels and forbidden energy gap. A free electron has continuous range of energy values that it can achieve. They're basically the state of the electron in the crystal. It can be quite different. Electrons of isolated atoms have a well-defined set of discrete energy levels. These discrete energy levels spread out into energy bands when several atoms are brought closer together. Now it can be evident from the figure, that is the part A shows the schematic representation of discrete energy levels of electrons, where here the energy bands are allowed to electrons and they are separated by forbidden energy. And the part B represents the schematic representation of discrete energy levels of electrons when the uppermost bands are overlapped. So the atoms in the crystals arranged in the periodic order, they are separated by a distance or a characteristic distance represented by d. Between the atoms, it is such that the energy band which is allowed for the electrons, they are separated by forbidden energy. However, as shown in the figure, the bands are overlapped, which provide ranges of allowed energies at the value of d characteristic of a different crystalline material. The energy bands possesses all energy states which are permitted for an electron. The highest occupied filled with the valence electrons known as valence band, and the unoccupied band is called as the conduction band. The valence band is represented by EV and the conduction band by EC as shown in the figure. Now it is evident from the figure that the electron can jump from the valence band to the conduction band only if it has a sufficient energy to cross the forbidden zone or the energy band gap, which is represented by Eg. It is also shown in the figure. So, the value of Eg can be calculated by measuring the absorption of light by a semiconductor material as a function of photon energy h nu. The sunlight can be absorbed by semiconductor materials only if this h nu is greater than Eg. At low temperature, which is shown in the figure A, there is no transition of electrons from the valence band to the conduction band. But when the temperature is raised greater than 0 Kelvin, as shown in the figure B, the electrons, they achieved sufficient amount of energy to cross the barrier and they moved from valence band to conduction band. This width of energy gap decides the amount of energy which is required to excite an electron from the valence band to the conduction band. The value of Eg for some important semiconductors is presented in the table, where the materials are tabulated with different values of energy band gap Eg in electron volt. Fermi level and Fermi energy. According to the Pauli's exclusion principle, each allowed energy level can accommodate at most two electrons of the opposite sign. At low temperature, all the available energy states up to a certain energy level will be occupied by the two electrons. This energy level is called as the Fermi level, or EF, which is represented in the figure also. The probability of occupation of an unoccupied energy state at an energy E can be calculated with the help of Fermi-Dirac distribution function, or Fe. So the expression for Fe is given by Fe is equal to 1 by 1 plus exponential of E minus Ef by kT. The Fermi-Dirac distribution function versus the energy states is shown in the figure, and the energy states above Ef, they have the probability of being occupied by the electrons, whereas those below Ef, they are likely to be unoccupied. Fermi energy level, or EF, is the energy at which the probability of a state being filled by an electron is exactly equal to 1 by 2. Categories of electronic materials. So students, the electronic materials can be classified in three categories. First is a metal, second semiconductor, and third is insulator based on their electronic band structure. Now the below figures shows the schematic of the energy band diagrams for insulator, semiconductor, and metal. Insulators are electrically non-conductive as they have huge energy band gap that is greater than 3 electron volt between the valence band and the conduction band. There is no free electron is available even at high temperature, thus they cannot make any contribution in the flow of current in crystals. Next is semiconductor. Semiconductors are the materials with narrow forbidden energy gap. At low temperature, they does not flow any electrical current and behave nearly the same as like insulators. However, at higher temperature, some of the electrons in the valence band gains sufficient amount of energy to jump into the conduction band. These electrons in the conduction band with huge unoccupied energy states in the vicinity can contribute to the flow of electrical current. Metals are the special case where valence band and conduction band overlap, and hence they show very high electrical conductivity even at a very low temperature. Electrons and holes. So students, here we will be discussing how the concept of the hole arises. As discussed earlier, at room temperature, the semiconductor material behave like an insulator due to the absence of free electrons. However, at higher temperature, some of the valence electrons attain a sufficient energy, that is, h nu is greater than Eg, and they can occupy the energy states in conduction band. The electrons excited from the valence band to the conduction band by leaving behind an empty state or the space or a vacancy in the valence band. This is called as a hole. So the holes in the valence band have a positive charge. Hence, the total current flow in the semiconductor is due to both the electrons in the conduction band and holes in the valence band. So the motion of electrons and holes in the semiconductors in the presence of applied field differs from the particles in the free space. The figure shows the energy momentum relationship for a direct band gap semiconductor. So now for a free electron, the energy and the momentum, they can be related by E is equal to P square by 2 m naught, where m naught is the rest mass or it's the mass of the free electrons. So we can differentiate between the electrons and the holes as the electrons, they have negative mass, they have negative charge, and the holes have positive mass and a positive charge. So now in order to get the relationship between the effective mass and the momentum, first we'll consider the energy and momentum relationship for the electrons present in the conduction band at energy close to the minimum EC, which is given by E minus EC is equal to P square by 2 ME star, where Me is the effective mass of the electron. Similarly, the relationship for the holes present in the valence band near the maximum energy EV is given by EV minus E is equal to P square by 2 m star H, where mH is the effective mass of the holes. So the effective masses of electrons and holes represents how the electron and a hole move in an applied field. So it is a tensor quantity for a three-dimensional band structure. Also, the expression for the effective mass is given by 1 by m effective is equal to 1 by h cut square d square e by dp square. Effective mass reflects the inverse of band curvature, that is, lower the value of effective mass, the larger is the curvature. It is very essential to assign the electrons and holes to their effective masses to describe their motion with the laws of motion of classical particles. So this table represents the effective masses of electrons and holes normalized to the free electron mass, that is m naught. So students, let us discuss about the direct and the indirect bandgap semiconductors. The energy-momentum relationship for the electrons and the holes in a direct bandgap semiconductor, which we have already discussed previously, that is E minus EC is equal to P square by 2 Me star, and EV minus E is equal to P square by 2 Mh star. So this is a direct bandgap semiconductor, and the energy and the momentum relationship for a direct bandgap semiconductor is shown on the left hand side of the figure. Now, the energy and the momentum relationship, the indirect bandgap semiconductor, is also being discussed. Before that, as you can see from this table, which shows that various materials which are having the direct bandgap. Now, coming to the indirect bandgap semiconductors, the energy and the momentum relationship for the electrons near the minimum of the conduction band is given by E minus EC equal to P minus P naught the whole square divided by 2 Me star. Similarly, for the holes near the maximum of the valence band, the energy and momentum relationship can be written as EV minus E is equal to P minus P naught prime the square divided by 2 Mh star. Hence, if P is equal to P naught prime, the semiconductor has a direct bandgap. However, if they are not equal, then it is known as the indirect bandgap semiconductor. The below table shows the various materials having indirect bandgap. Density of states. So here we will be discussing about the energy density of allowed states. What do you mean by the energy density? Energy density is denoted by N as a function of E, is defined as the total number of allowed states per unit volume and the energy in the corresponding band. In a semiconductor, the number allowed energy states are 0 within the forbidden gap and non-zero in the allowed energy states. Hence, it is obvious to know that how many states are distributed for electrons amongst the allowed energy bands. The density of states in a small range of energy, that is delta, in the conduction band can be written as N as a function of E is equal to the number of states in delta E divided by delta E multiplied by the volume. The charge carriers, electrons, and holes near the edges of conduction band and valence band can be treated similar to the free charge carriers. Hence, the energy density of allowed states near the edge of conduction band at energy E can be written as Ne is equal to 8 root 2 pi Me star to the power of 3 by 2 divided by HQ, this whole multiplied by square root of E minus EC. This is for E is greater than or equal to EC, where H is the Planck's constant. Similarly, for energy density of allowed states near the valence band at energy E can be written as Ne is equal to 8 root 2 pi multiplied by mh star to the power of 3 by 2 divided by h cube. This whole is multiplied by square root of EV minus E for E is less than or equal to EV. All these figures, first figure shows the band representation of a semiconductor. Next shows the corresponding energy density of allowed states for the electrons and the holes. Third figure shows the probability of occupation of these allowed states, whereas the last figure shows the resulting energy distribution of electrons and holes. These distribution of allowed energy states for the electrons and the holes. Now students, let us discuss about the carrier concentration. To calculate the carrier concentration in energy bands, we used the following known parameters. Firstly, the distribution of energy states or the levels as a function of energy within the energy band, which is represented by capital N as a function of E. Next, the probability of each of these states being occupied by an electron is represented by F as a function of E. So, the electron concentration represented by small n is equal to the integral from EC to EC max over FE NE dE. Similarly, the whole concentration, that is P, is equal to the integral from minus EC max to EC, the integral over FE NE dE. Conduction and the valence band carrier concentration. N is equal to, that is, N is the electron density, which is nothing but the total number of electrons in the conduction band per unit volume of the crystal, is given by the integral from EC to EC max over FE multiplied by NE into dE, where EC is many times kT larger than EF. The expression of F as a function of E for the conduction band can be written as Fe is approximately equal to exponential of minus of E minus EF by kT. After using the above equations and keeping the upper limit EC max equal to infinity, we will get the following expression for the electron density as N is equal to Nc exponential of EF minus EC by kT, where this Nc is called as the effective density of states in the conduction band gap, and it is given by Nc is equal to twice of Me star kT by 2 pi h cut square, this whole to the power of 3 by 2. Similarly, the density of holes can be written as P is equal to Nv exponential of Ev minus Ef by kT, where Nv is called as the effective density of states in the valence band, and it is given by Nv is equal to twice of mh star by kT divided by 2 pi h cut square, the whole power of 3 by 2. Intrinsic carrier concentration. For a perfect semiconductor which contains no impurities or lattice defects, this is called as intrinsic semiconductor. As the charge carriers are generated in pairs, the concentration of electrons, that is N, in conduction band equals the concentration of holes in the valence band. The product of the number of electrons and the holes, that is Np, it is a constant for a semiconductor under thermal equilibrium. So we can say that N is equal to P is equal to Ni, where Ni is the intrinsic carrier concentration. Also, N multiplied by P will be equal to Ni square. It is equal to Nc Nv exponential of minus of Ec minus Ev by kT. Or we can say that it is equal to Nc Nv exponential of minus Eg by kT. Also, Ef is equal to Ec plus Ev by 2 plus kT by 2 ln of Nv by Nc. Hence, for a pure and a perfect semiconductor, the Fermi level lies exactly at the middle of the valence band and the conduction band. So students, let us summarize what we have learnt in this module. Semiconductor has an electronic structure in which one is completely occupied by an electron, which is called as valence band, and it is separated by the forbidden energy band from the next band of the allowed states. This next band of the allowed state is virtually empty of electrons, and it is called as conduction band. The current in the semiconductors flows due to the effective motion of both the electrons and the holes in the conduction band and the valence band, respectively. Semiconductors can be divided in two categories, that is direct and indirect semiconductors, depending upon the impurities. These are known as dopants, which can control the relative concentration of electron conduction band and holes in the valence band when they are introduced in the semiconductor. Thank you.